welcome to finally another episode of Casted, here from IT University of Copenhagen, where we try to have conversations about, well, the borderlines between information technology and sometimes societal aspects. Not today, however. Today we take an unapologetically deep dive into the foundations of computing, the nature of computation, fundamental computer science. And the reason, well, there may be two reasons. I guess the ultimate reason is that I really love this stuff. And the proximate reason is that there is a brilliant new result by our guest, Nutan. Nutan, welcome to the show, Nutan Limaye.
Thanks, Thor.
Why don't you give us a brief potted academic bio?
Okay, sure. So I'm Nutan Limaye, your new colleague, for better or for worse. And so I joined ITU in September 2021. That's very recent. Before that, I was at IIT Bombay for 11 years as a faculty member. Before that, I did a small stint at Tata Institute of Fundamental Research. This is also in Bombay. Mm-hmm. And this was my postdoc stint. And I did my PhD prior to that at Institute of Mathematical Sciences. This is in south of India, Chennai.
In Chennai. Mm-hmm.
Yeah. Mm-hmm. So that's my journey so far.
Awesome. And the journey ended with you being a major computational complexity theorist. Was that clear from the beginning, or is this...
No, not at all. Not at all clear from the beginning. It was completely a coincidence that I landed up doing complexity theory or even theory of computer science. I was inclined to learn something about computer science. This was clear to me. And I was good at programming, so I really enjoyed programming. But specifically doing theory, this was definitely not a plan.
So it's just random encounters with just the right advisor or just the right courses? Or?
Yes, right mentors along the way, and some options which I thought were going to work out for me, they did not work out for me, and that also sort of helped me get here.
So it's a bit like me and algebra, right? I thought I would become I would do algebra because I saw those courses in math and I loved them, and then I took one more abstract algebra class and then one more abstract algebra class until it became clear that algebra did not love me back. So I then ended up doing theoretical computer science instead, and also fell in love with that. In fact, fell in love with circuit complexity, which is exactly at the core of this conversation.
Yes.
So just give us the title of your recent paper.
Yeah. So the current paper that I have, it's called Superpolynomial Lower Bounds for Low Depth Circuits.
Superpolynomial lower bounds for low depth circuits. So I promised myself that we're going to spend most of the conversation just trying to unpack those words, so that we understand what it means. Just for reasons of academic, candor and humility, there are co-authors to this?
Yes, of course. So this is a work done with Srinivasan, who is at Aarhus University, and Sébastien Tavenas, who's a CNRS fellow at Lama, France. Mm-hmm. Yeah.
So yeah, super exciting result. I'm surprised that this appeared in my academic lifetime. I guess once I started understanding this question, this seemed to be something that I would not see. But now it's here, so it's really awesome. I'm really excited about this because it's an impossibility result, and in some sense that is the most, intellectually valuable thing we can do in computer science, and I think that's non-trivial. And just understanding that these results can exist and why they exist, and maybe even how one goes about arguing about those. That's super exciting.
That's very flattering, and I think partly it's true. I mean, I'm happy about this result. There are many more one could prove, I guess, but certainly it fits in the theme of trying to show impossibilities in computer science. Yeah. So that's fun.
Exactly. So because I guess as a first approximation, science is about what we can do.
Yeah,
and
exactly.
maybe sometimes it's even about what we will do, and it's not so often about what we should do, because that's often much more often politics.
Yes.
But science normally is good at giving us a palette of options of what is technologically feasible.
Yes.
But this result is, in some sense, exactly the opposite.
Yes, it is about what is not feasible.
And
yes.
And even here, there could be many ways of misunderstanding what is feasible here. So there are entire books written about what computers can't do.
Yes. So maybe I can say a little bit about what is feasible, firstly, what we think of as feasible in computer science. So this is everything that we can program in some sense, right? Like you ask me how do I divide two numbers and one number by the other, and we can sit down and write a code for this. So this is feasible. And if I want to navigate from, say, from Diabuen to, say, I don't know, no port, then that's a navigation problem, and that's, again, something that is feasible. Now, you may ask, how fast can I navigate? What's the best way, etc.? So all these are feasible. This is within the realms of what's feasible by computation.
So feasible, tractable, computable, are these all the same, at least for this conversation? Or
So if we go to that point, maybe we can make a distinction. But for now, let's just say that anything that a computer can program is feasible for us. And we could refine this further by saying that, so I don't want to keep it completely at that computational level, because we are going to talk about complexity, which is resources on top of this. So, but just to get started, what's feasible is what a computer can do for now.
And that's also the historical progression.
That's
right?
the historical progression of what's possible, right? So, but as we progressed, computer science progressed, computers were actually developed, and so on and so forth. The notion of how many resources we need to spend in order to do computation also became relevant. For instance, if I want to, distribute some goods among people, and I want to do it in a certain amount of time, then is it doable, in that much amount of time? So the notion of either using time or using some other resource like energy or computational space like a mega computer, supercomputer.
Okay, so I guess for people who just follow information technology as users, it's intuitively obvious that computing time is one way that is expensive. Heat generated by computers, energy consumed by computers is another resource. Memory
space
storage
or memory
space.
Storage.
Yes, that's where we have these huge server farms and put them in cold places. And from the perspective of a computational theorist, and sometimes these are all just resources.
These are all just resources. And then you want to say, okay, given these many resources, can I compute a certain function or can solve a computational problem? So these are the kind of questions that started arising as, of course, computers became omnipresent. And so under the given resource constraint, is a certain problem solvable? This is a very natural question that one could ask. And there were lots of problems that were actually solvable, and that's why we have computers everywhere now. But again, there were certain problems which were just intractable. Even if you throw a fixed amount of resources to that problem, within those resources, the problem was just not solvable. And it wasn't for, smart people not trying to solve that problem. It was all the smarts of the world were getting together to solve certain problems, but they were just not solvable given the resources.
So let me unpack that a bit, because even the word problem here means many things to many people. So there's a tradition in philosophy that says that certain problems are computationally intractable, but not for the reasons that we are going to continue to talk about. But I just want to put a pin in that and just explain that this is not what we're talking about, even though the argument in some sense is reasonable.
Right.
So the argument there going in some sense that a disembodied computational device, such as an electronic computer, is not going to be, is not going to be able to emulate a human, for instance. So that is, we could view emulation of a human as, or navigate in the real world. We could view that as a problem. And then there is a tradition in philosophy that says that by virtue of the fact that the computer is, for instance, disembodied, or there are certain aspects of nature that we cannot turn into numbers, reify, I guess is the proper term, then for those, I guess, epistemological reasons, or is it epistemic? I could never understand these words perfectly well. So there is some kind of philosophical reason for why these things are intractable. That's not what we're talking about.
That's not what we are talking about. That's absolutely right. We are talking about... So let me say what a computational problem is. Should I do that?
You hit me, yes. Let me pretend to know slightly less about them.
Exactly. So I'm kind of talking to an expert, so it's kind of a little bit funny, but let me just pretend for now that I
will be the audience's avatar here. Please tell me about what a computational problem is, Nutan.
Right. So a computational problem typically can be thought of as you are given a certain string or an instance of let me just step back. Okay, let me give you an example, and then we'll move from there. Okay, so given two numbers, checking whether one divides the other or not is a computational problem.
Such as 15 and 3 and one of 5 times the other. So here the answer was yes.
Here the answer was yes, right? But you gave a yes instance to this problem. That is, the two numbers, 15 and 5, was an input instance to the problem. The problem is, given two numbers, does one divide the other? Say the first number is divided by the second or not, is the question. So that's the computational problem. Now, the numbers you gave me were 15 and 5. So yes, of course, the answer is yes in this case because 5 divides 15. You could have given me, say, 3 and 5. And in this case, well, if we are only working over integers, then it's not clear that 3 is divided by 5, right? It's not. So this is a no instance of the problem. Okay, so a problem is, like in this example, just given two numbers, whether one divides the other or not. And the answer, this is a decision problem. So what's a decision problem? You're just given a question and you are supposed to say yes or no. And all the inputs to this problem can be categorized into yes instances or no instances. So the pairs like 4, 2 is a yes instance to this problem, and say 10, 3 is a no instance to this problem, and so on and so forth, right? So,
and this is still easy enough for me to see because the numbers are so small that I can check these in my head.
Exactly. But you could have very complicated numbers. The first number could have thousands of digits. The second number could also have lots of digits. And then it becomes kind of not easy to just check with hand or just do the arithmetic in your head. But a computer can do it.
And they are happy to do that. It's insanely boring, repetitive work.
Exactly, right? And this you can even, the first program you can write in when you're learning programming could be for this computational problem.
Yeah, let's just spell it out. It's a for loop that starts with multiplying all these numbers systematically until I find the 3 that with the 5 gives 15.
Exactly, right? So you can do there are many algorithms to do this. The one you mentioned is the most obvious one that can come to your mind because we learn it in school. So this is something we don't think of it as programming in school, but of course we've learned it in school, right? So that's a problem. That's a computational problem. I defined it through example, but one can do this very rigorously. You can.
But navigating from here to Nørreport in Copenhagen is also a computation, but it's not a decision problem.
That's not a decision problem,
good.
but I could ask you the following question. Is it possible to navigate on, is there a road that takes me from Tiabuen to Nørreport with less than 1,000 steps?
Okay. Fine, or faster than 20 minutes.
Or faster than 20 minutes.
Using public... Okay, yeah, but that's a very realistic problem, right?
That's very realistic.
Can I get from here to Aarhus using public transportation in 3 hours, or do I actually have to rent a car, for instance?
Exactly.
Okay, good.
Right, so this is also a computational problem, in fact. What you can do to model this in computation is think of our, Denmark's map as a graph. Where you have...
Oh, but even graph is a difficult word here, right? Because graph means two different things.
Oh,
Network.
Yes. Network is better, yeah. So then there are all the cities and the, important places that we encounter along are the nodes in the network, and the links are the roads. The roads of the map are the links. And then every road comes with the time a car takes or a public transportation takes to navigate that edge. And so I won't go too much into details of how we can feed this as an input to a computer, but believe me that it can be thought of as input to a computer, and now this becomes an input to the problem. The answer of this could be yes or no. Again,
but I think it's believable, right? The problem is finite, it's write-downable.
Exactly.
And even with a very naive view of computing, you should be able to solve this by trying all possibilities or something in some systematic fashion.
Exactly. So if you are allowed to spend enough time and check all possibilities of things, then it's believable that this problem, you can give an answer to this question. Yes, exactly.
So, that was feasible?
Yes, that is feasible. These are all problems that are feasible. But maybe... going towards sort of infeasibility, I ask you the following question. Okay, so there are you look at the Facebook graph. So you have what I mean by that is all the people on Facebook are the nodes in the graph, and if two people are friends of each other, then there's an edge between them. Okay, so this is your network. This is the Facebook network, if you will, or whichever social media. I don't want to say anything more about Facebook, but just take any network like this. And so now here you could ask. So suppose I say that every person is allowed to hold a color, okay, and there are only 3 colors. So every person is supposed to be of a certain color. Say red, blue, or green. Yeah, and now I say that if 2 people know each other, they shouldn't have the same color. Okay, so this is the constraint I want to satisfy on this graph. Now, the question I'm asking is there a way for all the people in Facebook to hold a color just among these 3 colors, such that no 2 of them who know each other have the same color? Say if they have the same color, they get penalty.
This is a variant of a famous problem in graph theory where it's studied as map coloring, right? We have a map of countries, and you don't want neighboring countries to be colored with the same color.
Exactly. Exactly. So, here you can give a nice, interesting twist to this as well. But for now, yes, absolutely. You have in the country example, the graph kind of becomes that can be laid out on a plane. But in Facebook example, the graph could be
more complex. It's much more complicated.
Could be quite complicated than that. But exactly, it's the same kind of flavor of the question that no 2 neighbors have the same color, and we want to color the graph in this way. Now, this problem, also known as the colorability or 3 colorability problem, is a well-known NP hard problem. What this means is that, not for the lack of trying, we do not know any algorithm for this that we can code efficiently on a computer. So that's where this could be first example of infeasibility. That is, we do not know how to code a nice algorithm to solve this problem
efficiently.
Right. Efficiently.
Because we do know how to write graph coloring algorithms.
Yes.
I myself am the author of some, and I try very hard to make them better.
And it's amazing literature. It's just,
there's a huge literature.
I'm a fan,
and many of them, as you said, it's not for lack of trying. I've myself spent several clock cycles doing this faster.
Of course. So the question here is, I want to do this as fast as possible. Maybe, I want to do it as quickly as dividing 2 numbers.
So why is this not just a question of buying a faster computer?
Right. That's a very good question, right? So why can't I just get a better computer and just do this, faster? It could work if your graph had very few nodes to begin with. So
and
suppose
very few for you is what?
So let's take that I have today's most amazing supercomputer, and I have, say, 1,000 vertices. I can do this. It will be done in less than a day, and there's no problem at all. But the graphs we are looking at are not so small.
They have way more than 1,000 nodes, right?
Way more than 1,000.
Are there a billion people on Facebook?
There are. I think there should be more than a billion people, because people just create aliases also.
I see. Okay, so some of them are not even people, but fake people.
Yes, exactly. Right, but their networks can be very different from their actual...
And just to spell this out then, if you run this algorithm that works fine for 1,000, for a network of size 1,000, if I run that on a network that has size 1 billion, so there's a factor, I can't do this in my head, there's a large factor between these, right?
Yeah.
And the algorithm ran on, I don't know, as you said, a day on the small instance. How much longer do I have to wait on the large instance?
Right.
A week, a month, a year?
Yeah, so unfortunately it grows exponentially. Nowadays, because of COVID, we know what exponential growth is.
Very good, yes. Thank you to the virus for informing everybody about what exponential growth means.
So exponential growth means that, so this current algorithm, if it takes some amount of time, on more number of vertices, so from 1,000 to 1 billion, the time it will take will exponentiate, which is that it will take I too can't do this arithmetic in my head, but it could take like 100 years.
But I think it will take way more, right? I think it
Way
will
more.
take...
So if we actually write down the exact numbers, it will probably take something like 2 to the power of 5,000 or something like this. And this is because the original algorithm itself is going to take something like 2 to the n cube or something, and now n is growing. So
then that should be 2 to the 1 billion?
Yes.
And then we can do a number of computations per second?
Yes. So
I still think this will take several ages of the universe.
Yes. So if we actually do this correctly, and I can probably So this will probably take more than there are grains of sand, or there are
way more, probably more than there are elementary particles in the universe.
Elementary particles in the universe. So this is going to take forever, and this is also for the most powerful computer today. It's not just about not having computational power. Going back to your question, it's not just about throwing more computational power at the problem. It's just that the basic algorithm and the most improved algorithms as well, if the parameter that we are working with is kind of growing, is going to take a lot of time. So
waiting for faster computers is not going to work, but why can't we then just wait for a better version of people who write graph algorithms, right?
Yes,
why not wait for a better version of Thor, who suddenly has the good idea of how to do it faster?
Yes. So this could still be possible. This could absolutely be possible, and in Thor we trust. But the thing is that if, for example, Thor is able to solve the problem.
He will not, but let's take that as a hypothetical. You're very gracious.
If, say, we are able to solve this problem efficiently, then you would have solved several other problems which again are very, very hard in the similar spirit, also efficiently. So this would be a wonderful world to be in also for some other completely unrelated reasons, where you are able to solve many problems which we believe are hard and which we do not have answers to in an efficient ways of computing them. But all of them will sort of suddenly start becoming easy to solve.
So here you're referring to the theory of NP hardness?
Yes, I am. Exactly. So what happened was that not only this colorability problem that I told you about, but many other problems were together found to be linked to each other. Linked how? If one was solved efficiently, then the others were too. And this theory was, of course, it's ascribed to Steve Cook and Leonard Levin. Also, I think I should add, there is a long history.
But Richard Karp, yes.
Exactly. So Karp and Cook, and then Levin as well. So they all together came up with these set of problems.
But that's also a good anecdote, right? Because Cook and Levin were not fast friends while developing this.
No. So the history is very interesting. So all of this happened in the 70s. This was the Cold War days, if you recall. I'm
old enough, yes.
No, but even the world, I think hopefully the world remembers. So 70s, the younger generation also, I hope, remembers. So 70s were US and USSR, then the Russia-USSR, they were kind of in a pretty intense Cold War with each other. And of course, as war times are, you are kind of, a lot of people are busy trying to solve these navigational or large-scale problems in respective countries. So there is possibly a reason why such problems were also being thought of actively by a lot of people, a lot of computer science, large diaspora. That may be an independent thing. But what happened was, Cook, who was a theoretical, there was no computer science department as far as I know back then, but he was a computer scientist, he's a mathematician.
Maybe Stanford just started there?
Just started, maybe, yes.
Yeah. So maybe the topic existed, but they certainly...
Topic existed, of course.
But they thought about themselves as mathematicians, I guess.
Yes. Exactly, yeah. So he and, of course, Karp together came up with the ideas of hard problems, how they are linked to each other, reductions, and so on and so forth. Simultaneously, Leonard Levin, he was in USSR with no connection whatsoever to the literature that's being circulated in the US. And he independently discovered this, gave talks about it. There is a documentation of he discovering it completely independently. And I think this sort of a thing can only happen in mathematics where,
it's there's this beautiful quote that when the time is ripe, these good ideas pop up like in a spring meadow, the flowers everywhere at the same time.
Exactly. And I think like in a very dark way, the Cold War was in a way like a hotbed for such ideas, perhaps, because large-scale problems were important for some reason.
Oh, and of the connection between the history of computing and war is also super interesting. The first computers are built by von Neumann as a tool basically for the American nuclear bomb project in 1944.
Exactly. And of course also Turing, who was involved
also Turing. Oh, and then now we're getting the segue slowly to impossibility results. Because Turing famously also was involved in wartime activity in Britain in code breaking. Oh, this is very elegant because from code we can also go to crypto. So Turing at that time already was famous because before the war he had proved this amazing result in 38 or something in the 30s before the war about the Entscheidungsproblem. So I love saying that because I'm German and I can say that perfectly.
I cannot for the life of me.
We were still talking about feasible computations at NP hardness.
And then this whole story between Cook, Karp and Levin.
Good.
Yeah.
And do we go to impossibility now, or?
We could. So, I mean, this is computational impossibility where we are talking about resources, but you could also ask questions about whether something is just doable by a computer or not.
Oh, ignoring logical
the resources.
Right. That's a good distinction, right? So there are. Now we have already three different views of impossibility. There was the philosophical impossibility, which we just reject, not because it's not relevant, but because neither you or I have any authority.
Expertise on that matter.
But from the computational theorist point of view, there are at least two different flavors of impossibility.
Yes.
One is a more logical one that ignores resources, where things just can't be done full stop, even if we had not only the age of the universe, but entire ages of the universe.
Yes.
And that is Turing.
Yes.
And then there is the resource-bounded impossibility.
Yes. That can be ascribed to, at least the early stages of it can be ascribed to Cook, Karp, Levin.
Yes. And Turing is 30s? Give us the entire computational complex. No, give us a Turing 101 if you can.
Okay, so I'll try. This is a tough task.
Yes, it is a tough task.
Okay, so the thing is that so Turing is in the 30s. Okay, so he was studying in Britain, and he's a British mathematician from the 30s.
Oh, also maybe important, no Facebook at that time, no Google,
no Facebook,
no computers,
no lines of communication,
no internet, no computers.
Exactly, and the only way people communicated was this through writing letters to each other. And actually, as a positive side of that, we have literature to kind of trace back to some of the thoughts they had, because they had to kind of communicate these thoughts through really long letters. And there is also this Gödel's lost letter anecdote,
that's also fascinating.
But let's maybe not get there.
Let's park that.
Yeah, but those who are interested could look for the Gödel's lost letter maybe at some point. But so Turing was in his around the 30s was when he was discovering all these ideas. One of the main idea that is ascribed to Turing at the time is Turing machines. He developed a model of computation even before computers existed. So
before, let's say, digital computers existed.
Before digital computers existed. Of course, you can always say abacus existed from the Greek times and so on and so forth. But as the computers we know as of today, they did not exist when actually Turing came up with the idea of a Turing machine. Turing machine is a conceptual idea of a computer.
And when Turing said computer, he actually meant a human, right? So when Turing wrote computer, he meant, because there was a job description, you could work as a computer. Just as you could be a plumber or a dentist, and you could be a computer.
That's also interesting. A lot of women were computers at that time. So the computers were supposed to be people who added numbers,
who computed,
basically, right? Added numbers, multiplied numbers, or divided numbers, or whatever. Manipulations with numbers, and a lot of people involved were actually women.
Oh yeah.
Yeah. So this is an interesting facet also. But what he thought of as computers as automated tools or automated devices which can do computational tasks for human beings. So, and the way he modeled it is now known as the Turing machine.
And he called it the universal machine.
He called it the universal machine, and he kind of gave very elegant theory about how that universal machine can basically simulate any computation. So if I give Turing an iPhone today, he will be able to write a code on his Turing machine for what the iPhone does. Or if I give him my old, 8086 architecture chip, he'll be able to write a code for that on his Turing machine. So the Turing machine was sort of a device that could simulate every other computer.
And I think this is remarkable. So in 1930, he develops a mathematical model for universal computation and claims that any computational device that can be thought of is just a special case of my universal machine. And this was before computers. And then there are two or three generations of us building computers.
Yes.
And so far we have not come up with anything that is not modelable by the universal machine.
Yeah.
So his modeling aspect has been extremely stable.
Very robust, very robust. This is called the Church-Turing hypothesis as well, that anything that can be computed, can be done on a Turing machine. So they put out this conjecture hypothesis, and it has stood the test of time.
Despite enormous technological advance.
Enormous, exactly.
Good.
So amazing, yeah.
So back to the universal machine, and then so he defines this thing basically just as a lemma.
Yes.
To prove something much stronger.
Yes. Right. So now, should I be talking about? So you would like me to talk a little more about?
This is such a huge topic, right?
And I'm not sure which rabbit hole we are.
No. All of them are rabbit holes, right? and we like them. I guess there should be a way from impossibility results in Turing's world. And then I don't know. Maybe we can park Gödel. Maybe I find a logician at some other point of time.
Sure, yeah.
And so then from Turing, maybe one can go to polynomial time computation?
Okay, yeah. Perfect. Yeah. Let's try this. So what Turing did was came up with these amazing Turing machines and universal Turing machines and so on. Modeled computation even before computers were there. So this we have talked about already. So now it's easy to now talk about different types of these Turing machines and throwing. So one thing he firstly managed to show in for Turing machines was that there are problems that are just not computable by any Turing machine. Right, so this is the first, if you want to call it, the first impossibility result, that there are these problems, like we talked about the different problems. There are problems, they are not very hard to define, but which are just not solvable by any computational model, ever.
For enormously deep logical reason, right?
For enormously deep logical reason.
On some other civilization on a different planet,
yes,
they would come up with the same result.
They would come up with the same result. Yeah. So this also kind of connects to certain mathematicians that existed prior to this, Cantor being the main person. So Cantor had a diagonalization proof. So what he tried to show was something about sets and so on. So he was dealing with mathematics. And he was able to show that, there are two different types of infinities. There are natural numbers, which are of course infinite. There are real numbers, which are also infinite. But the two infinities are different. The infinities in the real world, in the real numbers, is substantially different from the infinity of the natural numbers.
And in some sense larger.
And way larger. I mean, there is no way to map this infinity to the natural number infinity to the real number infinity. He proved that, right? And this can be thought of as the first mathematical, not the first, but one of the mathematical impossibility result that nicely carries over to computer science. So this is a impossibility result. Why? Because it says not every real number is a natural number. Mm-hmm. So suppose somebody tried to say, show me how do I write this real number as a natural number, or as a ratio of two natural numbers even. can you say that there are real numbers which cannot be written as a ratio of two natural numbers?
Pi would be an example,
Pi
right?
would be an example. We know that now. We know that now. But can one prove that? Can one prove that there are real numbers which cannot be written as a ratio of two natural numbers? And Cantor was able to prove that. So that's one example of impossibility result. This was literally carried over as a diagonalization proof in the computational world by Turing.
Oh, you mean the melody of the proof? Because Cantor's argument is surprisingly short. For such a mind-blowing insight, it's surprisingly short and just takes
But it's exactly
five lines.
that. But I'm claiming it's exactly that by Turing.
Because,
Why?
Go ahead.
Because you can think of Turing machines as objects which can be described using finitely many bits. So, any program you give me, how does the computer read it? You just convert it into a string of zeros and ones and feed it to the computer.
Okay, the program is already a string of very, very finite alphabet, and then you basically just say my letters can be replaced by zeros and ones.
Exactly.
Good. So I give you that. Every program is just a sequence of symbols from a finite alphabet.
Right. Now, let's look at all possible problems in the world. Right? All possible problems in the world.
Can we restrict to computational problems? So
yes,
that we don't need climate change and world hunger, which are also problems?
Yes. Yeah, no, not those kind of problems. Computational problems. Yes, sorry. So, all computational problems. And it turns out that Turing machines are sort of like the natural numbers in this world, and subsets of problems are sort of the real numbers in this world.
So I guess the first part is believable enough, right? If I can just write out systematically all computer programs in a specific programming language and sort them as if they were in a library. So most of them will be nonsense, but all Python programs will be on that list.
Right.
And since that list can be enumerated, first program, second program, third program, they are just like the natural numbers?
They're just like the natural numbers.
I think that is believable. The other part...
Not so much, but one can think of it like this, right? Suppose I told you that instead of looking at natural numbers, let's look at subsets of natural numbers. Now, this is already a more complicated object, right? And computational problems can actually be thought of as subsets of natural numbers because they are putting together, say, all yes instances, right? So for a problem,
infinitely large,
but they kind of model a subset.
Okay, good.
Okay, so
like the 5,15,
5,15
and the 310 in the other set.
Exactly, right? So all the yes instances can be thought of as subsets again of problems. So now instead of listing problems themselves, let me just in my head list all the positive instances of problems as for the name say. I'll give that as the name holder for that problem. All the yes instances are the name holder for that problem. So now this starts to look like subsets.
Yes.
And now basically the same Cantor proof is...
Oh man, okay, so fine. Wow. So your ambition here was to actually, in a conversation, prove Turing's impossibility results.
Yes.
Over a cup of coffee. Yeah, I think that works, right? That should work. Yeah, because the subsets have a different kind of infinity.
Yeah.
Wow.
I mean, it is exactly that. Because if you now enumerate subsets and change the diagonal, you basically get the same thing. It's the same result. You can reword it now.
So having lost the entire audience by now, let's re-emerge.
Yes, re-emerge, I'm sorry about this.
No, this is awesome. This is brilliant. Just listen to this at half speed, and I think everything is in there. Wow. Good. So that was Turing's impossibility result, which shows that no matter how many resources we have, there are some problems that we cannot compute full stop.
Yes, exactly.
And that is sort of a mathematical view of understanding what computation is. But we are computer scientists, we care about the resources. And then actually in the 70s, so Turing happened in the 30s and 40s. Of course, Turing got very busy with the work related to the war, Second World War. And then he built computers after that.
Then he built computers, and von Neumann also built computers simultaneously. And so he actually came up with the first computer as well, the physical device as well. So, yeah, he's done amazing work, of course. So, but going forward in the study of impossibility results, in the 70s, people started to prove things like, suppose I give you some 1,000 steps to perform computational tasks. And then suppose I give you 20,000 steps to perform computational tasks. Can you tell me whether there is a problem that can be solved using 20,000 steps, which provably cannot be solved by 10,000 steps? Right? So this is also another impossibility question.
Yes, but now there's a quantitative part. Yes.
Exactly. So now the question is, if I give you some resource bounds and two different resource bounds, suppose more resources and less resources, can you prove that there are things that more resources can do that lesser resources just cannot?
Good, that makes sense to me, but I should be able to use some kind of counting trick, right? The number of Python programs, that's now the length of the program, which is not the same.
It's not the length of the program anymore.
It's not the length of the program, but it's the time that the program takes to run, and I can easily write very short programs that run for a long time.
Very short programs that run forever.
So where do I get from here?
Yeah, so this leads us to time hierarchy theorems, space hierarchy theorems, and so on.
And this is in the 70s.
This is in the 70s. They also kind of come from the diagonalization proofs. So all of these also can be thought of as more and more fancy versions of Cantor's diagonalization. Cantor to Turing, Turing to this diagonalization. And so these kind of results were also proved. But these were not explicit lower bounds. So I call a result a lower bound if it shows that a certain computational model cannot solve that problem. So
in that time frame.
In that time frame, or whatever resource you want to.
In that resource bound.
In that resource bound. So a lower bound result is a result which shows here is a problem that I cannot solve using these many resources. So that's a general lower bound problem, lower bound result. The paper that we are talking about, that we started out initially, is also a lower bound result. It says that a certain thing cannot be computed by a certain model of computation. So in certain amount of resources. Exactly, right? So in the context of that, now we are talking about come up with an explicit problem that cannot be solved using 1,000 steps or 2,000 steps or whatever, n square steps or.
And I guess when I first encountered this mode of thinking, my first circuit complexity course that I took, I think these were third or fourth years of my studies, I think the professor said, if you have shown this to a mathematician in the 70s, they would say, that sounds like a nice problem, give me 15 minutes and then I will find you one of these.
Exactly. So the thing is to prove existence of certain problems that are just not solvable using certain amount of resources can be done quite easily. So how? Consider a problem that set of problems that you want to show will consume more resources than this resource bound. Okay, you can say that look at all the resource bounds I have within the model I'm trying to work with. So if I have some, say, t amount of resource bounds or t amount of time, I can kind of compute all possible different internal states that the program will be in within these t steps.
I guess state is fine, right? So the values of the variables in a particular very restricted programming language, for instance.
Exactly, right? So you can always do this quite easily, that you can compute all possible different, if I look at a computer's run and I take a photo of it at every step, and it looks like something. The memory looks like something. The part of the code I'm reading looks like something. So suppose at every step of the program I take a snapshot. Okay, so how many different snapshots are possible for a program that runs for t steps? Right? I can count this number.
Yes.
I can count this number. And now, if this number is bounded, which it is going to be, then there is something that it cannot do. Namely, something that requires more snapshots than this.
By definition? Or?
By just counting that there are so many other tasks in the world.
Okay, good.
Which require so many more snapshots of computers. Maybe perhaps things that require t-square, machines that run for t-square time steps. So there's a counting argument.
Okay, there are way more problems than there are computing histories.
Exactly. For, say, resource-bounded histories, right? So if my bounded history is only for t steps, then there are all these snapshots, which we can call the histories of the problem. And now, there has to be something more than this. And you can actually say that there is something more than this. So these are the these are the kind of very easy to prove statements.
But they are not what we call constructive because they just established that there exists a problem. We don't know what the problem is.
Yes.
That is very hard.
That's very hard, exactly. So suppose I want to say, oh, this is the problem that can't be solved using these resources. We don't know how to say that most of the time. But we can say that there exist some problems that exist, computational problems, that cannot be solved within these resources. So these kind of results are called existential lower bounds. That is, there exist hard problems which cannot be solved using bounded resources. This is known, and this is known for most models of computation. Just because for every model of computation, there are limited histories.
But what we really want is a concrete problem like, I don't know, DNA sequence alignment, or some navigation problem, or the graph coloring problems that you mentioned about. Lots of problems in optimization, modeling, simulation, that we are frustrated about right now. For instance, simulating very complex climate models is an example of that. Right? It's a very complex thing,
system,
and our algorithms are not really good at incorporating all the data and throwing more compute after it, as it's called right now among the cool people. Doesn't really help us that much. What we really want is a better algorithm. We want people like me coming up with better algorithms, and we constantly fail. And it would be so nice to have a proof saying that this particular problem, this concrete problem that we want to solve, can't be solved faster.
Exactly.
And this we can't do in general. This has turned out to be really hard.
This has turned out to be really hard.
Why? It would be so nice, right? It would be so nice.
Yeah. Actually, maybe I should say why it will be very nice also. I mean, apart from it being like a very mathematically enriching question, there are concrete reasons why we want to show this. Right? So
you want to go crypto? That would. Okay. We promised ourselves to have an unapologetically deep dive into the nature of computation, but there are real good reasons for why somebody else than you and than other people of your disposition or mine would care about this.
Will care about.
Please tell us.
So, for example, the buzzword here is cryptography. Okay. So let me explain now why that's important here. So, for example, when we use our credit card, we are trusting a certain type of encryption in the process, right? I mean, we are kind of swiping something, it's reading part of our data, and then transacting money. And money transactions are very critical things. We lose money when we give money to somebody, right? And if there's a fraud, there's a problem. So cryptography is a way of securely communicating between two human beings via a computer. And what cryptography ensures is that many of these communications happen securely. That is, if there is a fraudulent party trying to listen on this communication, he or she will fail in creating a fraud in this transaction. So all of cryptography is sort of based on the assumption that there are certain computational tasks which are impossible or hard to execute.
In this case, decryption, inverting the crypto.
Exactly.
The cryptographic step.
Exactly, right? So decryption, not exactly decryption, but what I would say is that if we are able to show lower bound results, okay, so if we are able to say that certain functions are hard to compute under certain resource bounds, then that will ensure that cryptographic messaging is secure.
So, and therefore a result like that would increase the trust in one of the basic building blocks of digital society.
Exactly. So an impossibility result leading to secure communication, which we really care about in the real world.
So proving that something is impossible for us increases our trust in something else working.
Yes, exactly.
This is mind-blowing in some sense, right?
Exactly. It is amazing, right? This connection is beautiful and it's practical. I mean, it's as practical as it gets.
Yeah, the digital society would not exist today if we didn't have crypto. Everything we do that is useful, apart from sharing pictures of cats, all the other applications that are not sharing pictures of cats are based on crypto working. And crypto works because we have a shared intuition about some problems being computationally hard.
Exactly.
And what you are doing is to prove that these specific problems are computationally hard.
Yeah, there's a large community. I mean, you know them all well. So they are all trying to do this, trying to prove that certain problems are indeed hard to compute. Yeah. So this is one of the reasons why you want to show certain things are hard to compute. There is another less obvious reason, which is kind of de-randomization, but perhaps we don't want to go there.
Oh, that is even more complicated.
Yes, so maybe we leave that out.
Because then we need to understand randomized computation and...
Yeah, maybe it's not the best.
Let's leave that out.
Yes, perfect.
So then let's talk about what algebraic circuits are, because they are then a specific example of such a computational model.
Yes, exactly, right? So what we talked about are the problems like navigation and dividing one number by the other. But actually the dividing one number by the other is an interesting example even in the context of what I'm going to talk about, right? So basic algebraic operations are something that are omnipresent in computation. For example, if you want to find out whether one number divides the other or not, this is an algebraic computation.
So plus and times.
Plus and times and division, if you like, or you want to ask whether, whether what is the determinant of a matrix, or you want to ask how fast can you multiply two matrices, or how fast can you multiply D matrices.
And now we're talking about machine learning suddenly. If there are D matrices involved, it's deep learning. Yes.
Right. So this is all very important things. And these are actually algebraic objects because...
Right, so unsurprisingly, at the core of all the applications that we see today, including cat videos, there is just plus and times, sometimes on numbers, sometimes on larger objects like matrices.
Yes. If we make it quite vague, it's really that, right? So if you have... so the basic operators that we are that one deals with in many aspects of computation is plus and multiply. And you want to see how far can putting together these plus and multiply operators can go. So that is what is algebraic computation. So the area of algebraic complexity theory, which is what kind of is one of the areas that I work on, asks the question that, okay, if I want to put together multiplication and addition operators and compute, say, whatever can be computed using multiply and plus, so say arithmetic formulas, or like a square plus b square minus 3ab, etc. All these kind of things, how fast or how quickly can I compute them just by using plus and multiply operators? You are allowed to use minus, sometimes you are allowed to use division, but that's it.
So how fast now means how many applications of the more primitive operator, right? You have a more complicated expression like a to the 5.
Yes,
which I obviously can compute by just taking a times a times a times a. That's 4 multiplications.
Yes.
But can it be done with fewer multiplications?
Right.
Clearly not, Nutan.
Oh, clearly yes, Thor. So you can do it by just powering, right? Like you take a and a, multiply them with each other.
I have a squared.
You have a squared. Now multiply a squared with itself.
And then I already have a4 and
a4. So you didn't have to do this 4 times. You could just do it 3 times.
Good.
Right? And this kind of speeds up things.
But this is mind-blowing, right? It's mind-blowing that the task of computing a to the power of 5 does not require 4 multiplications, because the description of the task...
Yes.
Implicit, the definition included the algorithm, but there was a better algorithm.
There's a better algorithm, right?
Yes.
And this happens all the time.
And this is just a microcosmos of everything that is beautiful and nice and interesting about algorithms.
Exactly. That you feel like, oh, this seems like the most obvious things to do. Sometimes it's just wrong, that's one thing. But but even if you are wrong, you may not be doing it the most efficient way. And like in this example we saw, you could have done it with just 3 multiplications. 4 were really not necessary, and this scales up. This scales up quite well, in fact.
Okay, and then the question you ask is, if we can do it with 3, can we do it with 2? Or in general, if we have a large expression, algebraic expression, how few steps can we compute it in? Now I ended a sentence with a preposition, which is bad English. But
Yes, I keep doing that all the time. So sorry about that. But so this is exactly the question that you're given an algebraic expression, and now you want to ask how quickly can I compute it? Quickly can mean two things here actually. One is how many operations I use, and the other could be how many cascading of operations I use. Like I use a bunch of operations, they feed into yet another layer of operations, then yet another layer of operations. How far or how deep do I need to go?
Oh, this is some kind of parallelism, right? Some of the operations you can do in parallel that don't depend on each other, but you have to wait for the computation of the first layer to be computed in order to do those on the second layer. Good.
Yeah, but at the same time, the things on the same layer can be simultaneously computed. So that's the parallelism here.
If I had enough computers.
If you had enough computers, exactly. So there are these two notions of what we mean by efficient in this kind of algebraic computations. One is how many operators you need, and then how many cascading or how many layers of computation you need. That's kind of the depth of computation.
Depth.
Depth, yeah, exactly.
Right. Yeah, I learned this in circuit complexity. Time is size, and parallel time is depth.
Exactly.
Yeah.
Exactly.
Good.
Exactly. So that's the kind of efficiency we are talking about. These are the resources we are talking about. So all along we were talking about resources like time and space. Here in this model of computation, which is just you put together plus and multiply operators. Now the resources are how many operators you need to use. That's one. And what is the layering? How many of how many cascading or how much feeding of one layer into another, and to what depth do you need this?
So we've been making enormous progress in trying to understand the title of your paper now,
yes.
right? So remind us again, just to see how far we are. Polynomial time lower bounds.
Superpolynomial lower bounds.
Superpolynomial lower bounds.
For low depth circuits.
For low depth circuits.
So we know what...
Low depth algebraic circuits.
Algebraic circuits, yes. So we don't call it algebraic in the title, but it should be.
But they are algebraic circuits.
Algebraic circuits. So we talked about what circuits are vaguely. That's just putting together these plus multiply operators.
They're just glorified formulas in some sense.
They're just glorified formulas, right? Exactly, right? And then depth, we talked about low depth. Low depth just means you don't cascade too many times. And we talked about lower bounds. So now only superpolynomial is the only part.
Now only superpolynomial, which sounds like a bit like a superhero.
So yeah, I think superpolynomial is kind of, when you don't have too many glorious terms, you kind of just coin something. So, but superpolynomial just means strictly more than polynomial.
It just means more than polynomial, right?
Yeah, exactly.
But not necessarily exponential. Just to spell this out, I actually understand this. But
yes, exactly. Of course, yeah.
There is something between polynomial and exponential.
Yeah.
There are functions between those.
Exactly. And this is in fact, our lower bound is not exponential in some situations. It's only superpolynomial, that is strictly more than polynomial, but not exponential. Yeah. But this is a function. Superpolynomial is a function that stays between polynomial and exponential. So
n to the log n would be an example.
Yes, n to the log n is an example. N to the log square n, and n to the any polylog n in the exponent. N to the square root n is actually n to the square root n will already become exponential. So let me take that back. But I mean,
but
it depends on what you.
I guess for most people, exponential just means very fast.
2 to the n,
but we have a very precise taxonomy of these very fast.
Yes,
and superpolynomial is very, very, very fast.
Yes, superpolynomial is faster than polynomial. Polynomial is what we call efficient. Efficiency means we should be able to solve certain things in polynomially many resources. And if you're not able to solve, that's a lower bound. You're saying that you need to throw more than polynomially many resources at this problem to be solvable.
And you know the problem for which this is true?
Yes, indeed. It is multiplication of matrices.
Oh, that's super concrete.
That's it. You take D matrices, each is n cross n. That's your neural network if you want. It's n cross n
over
D
the integers?
matrices.
Or?
No, you have variables now. So it's not integers, but it's variables. So every matrix has a fresh set of variables. And now you want to just multiply these matrices out and maybe find out the 1,1th entry of this matrix that comes up.
So I learned to do that in linear algebra class. It's whatever matrix computation and cube maybe naively, and then I repeat that d times.
Exactly. But what our result says is that, so this is doable if you are allowed to have lots of cascading of layers of plus multiply. In fact, if you have log n cascading, so let me not say log n, but if you have sufficiently many cascadings of plus multiply, you can solve this quite efficiently. What we show is that if you have just 3 cascadings of this, then you cannot solve it.
In polynomial time.
Using polynomial.
I guess there should be some
operators.
argument saying that if you have exponential or maybe super exponential size, then this should be okay, there's a meta theorem that shows me how to do that. I can just list the...
Yeah.
Okay, good.
Yeah,
fine.
And in fact, there are concrete upper bounds for this problem using just 3 layers.
Yeah.
But we are able to show that, in fact, you cannot do better than what is the most obvious algorithm to solve this. So you come up with the most obvious algorithm to do this using, say, 3 layers of operations. Okay, that's like a divide and conquer strategy.
Maybe that's even obvious to me how you do that then.
It's like
it's a sum of products.
So you can basically do it in some product quite easily. Why? Because just take these D matrices and kind of break them into square root D chunks each.
Right.
And now kind of recurse.
Okay.
And this sort of an idea gives...
Okay. This is believable to me. So I guess
exactly.
the tools that I teach in my algorithms class should be enough for me to see how to do that.
Exactly.
And then you say that what I can come up with there after teaching my own algorithms class and understanding what's going on there,
modest,
you can now prove that nowhere, not only on this planet, but any other planet in the universe,
you can't do better than that.
You can't do better than that. That's
exactly.
amazing.
Yeah. So, but that's what the result says.
Yeah.
So it's for a concrete problem, and we are able to say that it cannot be better than what obviously a person will come up with.
And I guess then that is maybe the other argument, besides building trust in hardness of computation for instance, crypto, the other reason to do this is that it shows us, it closes off avenues of improvement.
Exactly, right?
Because we don't want 1,000 people like me spending useless clock cycles trying to come up with a better algorithm, a better mousetrap.
Exactly, right? So for humanity, say that we shouldn't be spending our clock cycles on things which we know are computationally not possible. So also being able to say something that, whatever you were able to do within learning the algorithms course is something that is the best you can do, is another, it may sound a little pessimistic that, this is all, is there nothing more to it? But it's also saying that, okay, maybe pay attention to other problems which need more attention and maybe are also feasibly attackable. And
great. So there is the just pure pleasant part of having this aesthetic result, which is just internally motivated, super nice math, and it just makes you happy to see it.
Yes.
Then there is the societal aspect, which is about trust in absence of computational solutions.
Exactly.
And then there is the scientific hygiene or something that tries to prevent us from pursuing avenues that are silly.
Exactly.
Awesome.
So that's it, I guess.
That was it. There was an entire course in computational complexity. Very pleasant. I got a lot out of this. Anything else you want off your chest?
No, that's it, I think.
We have everything. Okay.
Yes.
Thank you very much, Nutan. This was super entertaining.
Oh, yeah. And, I hope I hope it went well.
Everything is Googleable, right? Because these things are now core computer science. And if this is just an entryway to pursuing this,
it could also be thought of as just listen to the keywords and maybe, if you find any of them interesting, go back and Google kind of a thing for most listeners, I guess.
Thank you very much, Nutan, and thank you all for listening. Bye.